Aloha?
Aloha.
Good, I got an answer. That means I can keep going. So, I am going to be talking about biochar ovens and mostly about the JRO or the Jolly Roger biochar oven, because that looks like the one that's going to be of greatest utility for smallholders around the world, because I'm particularly interested in climate change mitigation, and by twice over can we get biochar into the ground if we get smallholders making it than if we get everybody on high-tech, big commercial things. At least that's what the models are telling us. All right. Okay, just in general, the pictures I'm going to go through. Here is what I am from. I don't want to use the word promoting, but I try to teach people about at the beginning. And this is a simple updraft, 55-gallon or 200-liter J-row with a gap top afterburner at the top. You can see at the bottom, this is, well, there's one mistake. There's an extra hole in there because there get to be a lot of holes in the pattern. But it's called the circled square. And the only reason I'm promoting this is that it's simple to make. All you need is a piece of string, a straight edge, and a marker. And of course, whatever you're going to drill the hole with. So it's consistent. Now, there are many, many different designs that you could put those holes in. All I ask is that when you come up with a magic design of your own and you want to name it, fine, but run it side by side to see if it makes any difference. And if it's a lot better, we'll use that. If it's just the same, let's keep something so we can compare. This is a simplification of the test bed you see over on your right side, which was designed up in Mongolia after we saw John Rogers' film on Facebook or YouTube. And it was a test bed because I mean, all of us who are designing these things, not all of us, but most of us are not engineers. We're just dumb lucky. And John Rogers got his to work, but it wasn't working perfectly. You could see that some places he just lucked out. Other places he didn't quite have it good enough and it was smoking a little. So we wanted to try to perfect it. So you see on the bottom, there's a 55-gallon drum in the middle between two 1/3 sections of a drum on top and the bottom. The bottom is an air chamber, and you can regulate the amount of air coming into the air chamber with that slip ring. And but the primary air holes are that circled square design. On top you have the afterburner chamber. Again, there's slip rings on the top there to regulate the air coming into that. In the standard design we have now, that top chamber has been eliminated, and you just use the secondary air comes in a gap underneath the what you might call the lid. And also the bottom chamber has been eliminated, and we just have 3 stones to allow air to come into the air holes. Wrong way. All right. This is the first burn with this design. You can see from, and it's always nice with your first burn in a barrel, you get a very good idea of what the flame front is doing. And so the first top 10 centimeters is part of the afterburner chamber. So the thing has been burning maybe about 1/6 of the time. But you can see already down on the bottom, there are hot spots. So this theory of how TLUDs work came from cook stoves that have very nice uniform feedstock. When you get up to the 55-gallon drum size with the width and very often heterogeneous feedstock, the theory tends to start to break down, and you get burning not a well-behaved flame front, let's say that. But it still works. Here's the test bed, and that's the former one had a load of wood chips, which should be fairly uniform, but you could see that the flame front was not well behaved. This is a load of dried cow manure, and it was the size was very of each piece was very heterogeneous. Yet you can see the flame front is fairly well behaved. It's down there almost finished, because remember there's that primary air chamber down below. So it's almost finished its burn, and it's almost what you get pictured as a one flame front. And I can get into that a little bit later. Here's what the temperatures look like. The top red one, the probe was put in about 18 centimeters above the top. So it's just below the afterburner. And then as the feedstock charge gets charred, it slumps down, and then the probe is, towards the end, is in the afterburner. The bottom one is at the 18 inches above the bottom of the feedstock chamber. And yes, it is at 0 with Mongolia in the fall. But so you can see then that as time goes by, the flame front is coming down. And then as the flame probe gets near, it starts rising up and passes above even where the afterburner is. And that's because probably you're getting quite a bit of carbon burning near the bottom, where you get a lot of air in there. Okay, this is that circled square design. You take a piece of cord, you wrap it around the outside, then you hold the where the end meets your cord. You divide it in half. You put it down there again. That gives you the point directly across from where you started. Then you take that half and divide it in half. Now you've got your 4 points that determine the maximum square you get it there. You divide the sides of the square in half and in half again. That gives you 5 columns, 25. You put 3 in the gap, and that gives you 37. And so nobody needs to know the geometry of why that works. They just need to spend 5 minutes doing it, and they can do it on any size. And then you drill your holes. In this case, if you're familiar with barrels, you'll notice that this is on the lid of the barrel. So I flipped the barrel over. The open mouth is now down. I've cut off the bottom and put the stack on the bottom. And actually, I put it on the bottom of the bottom, so that you have to tip the bottom over to get the stack up. What that allows me to do then is change the size holes in the pattern, so I can get different amounts of primary air and not have a whole bunch of barrels. All I have is the lids. I swap them in and out. Then when you want to take your barrel someplace else, you flip the lid so it fits nicely, or the bottom so it fits nicely, and the stack is down in the barrel. And you can put extra stuff in there, and it's a nice unit to move around. Okay. For those of you who haven't worked with them, I'm just going to go stepwise through making one. You see the components. And this one was the first design, so actually the stack is put on the lid, and the holes are drilled in the bottom of the barrel. So you'll have the lid of the barrel with the stack on it. That's the top of the afterburner. The wood chip load there, you can see, this one is quite full. It's probably within 8 centimeters of the top. So between the top of the barrel and the top of the feedstock, that's your afterburner chamber. These bars down here are what give you your gap. These are probably the biggest gap bars you'll ever see. There was actually a metal building beam, but it just happened to be around, so we made it out of it. Usually we just use a piece of angle iron. Gives you your gap. Being a frustrated Boy Scout, I use these little TP fires to get it started. But now, since we're running experiments with cow manure feedstock, we don't want the wood char contaminating our results. So we just mix it with a half and half, 91% alcohol and some vegetable oil. Soak it a little bit in the top, throw a match in, and it lights off very easy. However you get the top going, once these coals are spread around and you're burning, you put in your gap bars, put on the top of the after chamber, and then you get, you can see through the air gap what's going on in your afterburner, and this is what you use to monitor the machine. That and how the barrel's heating on the outer edge. And when the orange flame is no longer present, it means you've done all of your destructive distillation and your pyrolysis gases are no longer being generated. It's still very hot in there. There's to my eye, a ghostly blue-gray flame, more gray than blue. I don't know why people keep saying it's a blue flame. You can hardly see any blue in it. But that's the carbon monoxide burning into carbon dioxide. And now you're just burning up your char. So you put it up. If you are going to use your biochar yourself, as most people will be who are using this thing, and particularly if you're going to incubate it in compost, as Dr. Anderson mentioned, if you get a big piece or you have two pieces with flat surfaces and they kiss up, they're now very thick, and you'll get a little bit of this orange flame persisting. And if you wait for that to stop, you've burned off a lot of your biochar. So it doesn't really matter if you have some torrefied wood, particularly if you're mixing it with compost. So when you also notice a difference in the characteristic of the orange flame, it starts out very lively, probably methane and hydrogen mostly burning. And then it gets to be kind of an old, lazy flame there. That's the heavier oils that have been vaporized. So after you've gotten used to it,
I'd just like to add one little observation.
Go ahead.
An important concept is that wood burns at one temperature, typically 400 to 600 degrees C. When it gets down and the char starts burning, that temperature goes up to above 1,000 degrees C. And this is very, very hard on these materials. So it's really more important to stop it when the first part of the pyrolysis front gets to the bottom, because that's the point at which you're going into this fairly aggressive destruction technique. These are 55-gallon drums. They were intended for room temperature. You'll know that most charcoal burning devices, hibachis and stuff, are cast iron. So this is really the reason we urge people to not wait for that last bit of yellow smoke to stop, because you've shortened the life of the bottom of your devices unjustifiably. Thanks.
Okay. Okay. What am I doing? Oh, this is just to show you that it's almost impossible to follow those directions as well-meaning as they are, because I've got 3/4 of a barrel full of raw feedstock in this right now, and it's already burning charcoal at the bottom. So if you're not going to have an air chamber at the bottom or regulate whatever's causing this flame to run down there fast, you're just going to have to use up more barrels. Although I think since we take good care of our barrels, particularly the ones when you can take the bottom off, you wash them out, you dry them, and you keep them inside and dry, I think they're going to last longer than anybody thinks. We're going to have 60 burns in this set of experiments. We'll find out how many one lasts. We're keeping track of that. Okay, we went through the orange flame. Now, when the orange flame goes out, or about goes out, or the lively fire stops and you just got the lazy fire left, you take off the top of the afterburner, take out the spacers, and this is the lazy man's way of quenching. You just dump some water in, stand back, and stand upwind. Because when that water hits 600 degrees to 800 degree charcoal, steam rushes out with a lot of ash or biochar in it, and you don't want a face full of that. Then you dump it out, in this case, and further hose it down. What we do now, because we're running experiments, we want to know exactly how much char we have in there. We dump it into a hanging scale, which is a little bit tricky itself, because it's you got 1/3 of a barrel full of hot ash, and you got your scale up here, and you're trying to weigh it, but it can be done. You take a hot sample out of that to get how much ash you have in your char. And then I dump it into a half a barrel of water. So we're very conservative on water, and it gets it all out fast. You don't get any burning after that. Like some of the other feedstocks you can do, this is bamboo slats. They're made the length of the feedstock chamber, and you pack them in there like this, and then you spread your coals on the top, and it burns down, and you get a fairly good load of char out of it. Okay, this is Joss's. Is he here? No. I put this in there. This is not a biochar oven. This is a charcoal filter or filtering charcoal oven, because it's designed to get up to 900 degrees, much hotter than your chars. Now he puts out this design of how it works, but I think we are all agreed, and he has agreed too, that you don't have this nice flame front. In fact, I don't have his temperature probe, but if you look at the, if he puts a probe in the middle, it goes immediately up to 900 degrees within about 10 or 15 minutes. It stays for the 2-hour burn, and then it drops back down when he quenches it. And it's up at 900 degrees all that time. That's higher than your pyrolysis temperature. So he's burning charcoal all over inside there to get that high temperature, because he has 300 holes in there. So he's just, it's natural updraft, but it's drafting in a lot of oxygen. And yes, it probably won't last very long, because I went up there and saw the other.
I got to defend Josh's reputation. He was doing this right up in the parts of Thailand that are not particularly well controlled, and he made it with like a quarter that many holes and ran it, and it didn't run well. And tomorrow he's got to show it to the warlord who's coming up to be impressed. And he's figuring, if this thing doesn't work right, this guy's going to take me off in the jungle, and that'll be it. So he spent all night long drilling 300 holes, and he got to the safe side, which was more than he needed.
But many of us who aren't engineers and chemical engineers happen to have this angel on our shoulders, and it's just dumb luck. And he wanted filtration charcoal. He didn't want biochar. And by luck, God sent down a warlord, and he got it by accident. This is in Costa Rica at the Sea-Char's site, and they with Hugh and I think Paul, you were there too.
Not at the same time with Hugh, but yeah, I was there.
Yeah, so this is their adaptation and their idea of what a J-row would look like. And this is basically the afterburner chamber, I take it. And then it's covered with this. I don't know how they monitor it, since it would be difficult to see the flame, but I wasn't there, I don't know. They have a little thing on top here to, I guess, to prevent it from raining, but that one that you saw me making in Thailand with the bamboo, that one ended with an awful cloud burst, and the thing kept going for quite a while, even in the cloud burst.
Just a quick question, is there any concern with the galvanized coating burning off of those?
Well, I wouldn't stand downwind of it.
Okay, yeah.
It doesn't actually catch fire, but it does change. And there is a concern if you put your chimney together using those aluminum pop rivets, they'll burn out at the bottom. But it'll hold it for a time or two, and then you put in a steel bowl.
Can I comment on the zinc from the galvanizing? The dangers of galvanizing is if you're putting arc welding temperatures on it so you don't weld it, but what you're doing is just oxidizing it, and zinc oxide is that white stuff that you put on your nose to prevent you from being sunburned, not particularly toxic. I mean, like you said, don't stand downwind from it, things like that. But
okay, we have something important to try to get through. This is what I lovingly named the Hopeful Dragon. This is what happens when you use forced air, and a lot of it, and I'm not belittling it. Forced air gives you a lot more control over how much air you have. In other words, I think here you've got 300 holes worth of air coming in. And you can control it if you can control your fan. You don't need such a big fan. You can see the small little fan. This again is more like that test bed, so you have an air chamber below, a fan putting the air into there, and then that circled square distributing the air around it. Once it gets going, this is that fan setup. You can, this is a Hugh McGuffin special. Where did this kind of fan come from?
eBay is where everything.
Well, I mean, yeah, but what was it?
They get sold out of China. These are about $4, and they're all over the place. These are little computer fans. There's
Okay.
every size known to man a computer fan.
Okay, so this is a rather big computer fan, but you can regulate it by moving the lid of that tin can around the air intake. The other can with the black tape on it is just to fit it into a second can. And you can see that second can here, but the fan is not there. Once it gets going, it carries on by itself, drawing enough air into the chamber. And whoop. Okay, now we're getting into what I call a hybrid stove. On the bottom there with the rusty looking can, which looks like in the background, that's the standard T-lud we're talking. This has a forced air draft. You can see at the very bottom there that fan with a tube blowing it in there. Above that is another 55-gallon drum, but inside the 55-gallon drum is a 35-gallon retort full of wood that you want to make into fairly nice retort char. And so you're using the heat from the T-lud. It's not being wasted because it's driving that retort. Now, most of the time you're told about what good results you get by the conversion rate of feedstock to char in a retort. And they conveniently forget they've burned about that much wood on the outside. So when they tell you that they got 30% out of a retort, and divide it by half roughly. But here you're using the heat of the T-lud, and you're getting the T-lud biochar if things are balanced right. And you see once they got it going, they didn't need that extra fan going into the gap, and they didn't need the extra fan at the bottom even. You can get quite a bit of draft up there. Even though at the gap, of course, you've broken your suction. So when they put these great big long chimneys up the top, in my mind, there's a question of just exactly how much draw functional draw they're getting down in the feedstock because you have the bracket. What about 2 minutes?
2 minutes.
Oh. Okay. And this is how much holes he got into when he was able to actually run a hybrid there and make thick wood for fuel char.
Who is he?
Josh. Now, handling the feedstock, here's brush. Great feedstock, but it's kind of hard to see how you're going to get that uniformly into a 55-gallon drum. If you're Doug, that's no problem. You put a come-along on it, force it into a fairly dense tube, and use your chainsaw to cut it up. Okay, I'm going to go very quickly through these. These are different ways to get your primary in. Instead of having it come in from the outside, you blow it on into the inside. This is a McGuffin special. That's the tube that went in there. It has these slits in there. Okay, I started out. This is also a biochar oven. This is a retort, but the fuel that they had and they wanted me to use, and I wasn't thinking, is sawdust. Anybody who knows that you cannot make char out of sawdust in a standard thing. But you can make it 5 centimeters around the edge. So you make instead of a barrel, you make it a 10-centimeter box with holes in the side. You put the fire underneath with a cowling around it, and he's pulling out these retorts, and he's snuffing them under the dirt. And this is some of the char, and it works well with sawdust. If you take that retort, and instead of sawdust, you use sticks of wood, or the little pellets there are goat manure, and the big brown mass there is cow manure. That kind of retort works fairly well, although you are burning about as much biomass outside as you have inside. People say that you cannot do sawdust or rice husks in a tilad. You can, if you're clever and you've had some experience of making a retort that's only 10 centimeters wide. You put a vein of, in this case, rice husk in the middle of your tilad, and then on the outside of that you make good tilad fuel, in this case corn cobs. Pull out your baffles, and now you have that vein. And when you light it normally, the tilad works on the outside. It's enough heat to run your virtual retort on the inside. It makes good char from both. But one thing that, as I say, we are interested, these are primarily for smallholders, and in the third world, that's small farmers. What's your distribution of small farmers in the world? Gray is Asia. Dark gray is Africa. In the Americas, it's a slit. Europe is the white wedge. So if you want to get char in the ground by small holders, Asia is the place to go. Africa needs it. They need somebody over there. And why do we do it? These are herders. They want to stay herders. Here's the tilad in the back that we make biochar with it and give them an extra income, and actually vegetable gardens and things, so they could stay living here where they want to. And that's the end.